Okay, so thanks for the introduction. As you said, I'm doing my PhD at the Institute of Electronic Sensor Systems in Graz, Austria, in cooperation with the company Electric Sensor Technology, which is a startup. The topic of my presentation today is using MEMS acceleration sensors for monitoring blade tip movement of wind turbines. So first of all, I would like to start with a short introduction why monitoring the blade tips is important in wind turbine engineering. So in general, monitoring wind turbines helps three different purposes: to minimize maintenance costs, to increase the lifetime of the turbines, and of course to guarantee safety during operation. So during the last years, we have an increasing size of turbines. With this, of course, we also have greater loads and forces acting on the blades. So for example, you can have an uneven wind profile, which is called wind shear. You can have, of course, acting gravity on the blades, especially when they're getting larger, and you have turbulences affecting the whole turbine. So with this, the risk of unnoticed damage is also increasing. So this is why we need monitoring in for wind turbine blades. So what measurement principle did we decide for? So we decided to place accelerometers on the tip of rotor blades to measure the maximum deflection. We decided to put them at larger than 90% of the blade length and on the outside of the blade, because on the inside of the blade there's support structures, so you can't place sensors on the tip. And also, of course, if you place them on the outside, maintenance and retrofitting is more easy. How did we do this? We integrated a MEMS sensor element into a sensor of earlogics. You can see the sensor over here mounted on the rotor blade. This sensor is very thin and flexible, so it doesn't influence the blade itself. As well, power supply and data transmission work wirelessly, and we conducted burst measurements of 26 seconds to stay within the, of course, restricted energy budget. So now I'm coming to the feature development. That's kind of the core point of our work, which is split up into three different things. So first we have wind effects and alternating loads, which we want to detect. So we did a simulation of the rotor and then developed features which can be used to detect those different effects. So which different wind effects do we have? In general, we focus on stationary processes, so we didn't take any transients and, for example, turbine steering into account. So we focus on four different effects. First, we have wind shear. This means that we have different wind speeds across the vertical profile of the turbine. Then, of course, we have gravity acting on the blades, always downwards, no matter on which position the blade is. So we have a sinusoidal decrease and increase of bending. Next, we have yaw. So normally, the turbine is directed into wind direction for optimal energy harvesting. If we have a mismatch of both directions, this is called yaw. And last but not least, we have the tower shadow. So if the blade passes the tower on the bottom, the flow is decreased near the tower, which of course also has an effect on the blades. So the next part was the rotor simulation of these effects I showed to you. So the starting point are the wind speeds and loads acting on the blade. According to this, we have a bending on the blade. So if you have, for example, larger wind speeds on top, you have larger bending on top. And this changes the absolute position of the sensor, which is mounted up here on the blade. The sensor itself measures the centripetal force as well as gravity. So these two are influenced if you have different bending across the circle of the turbine. Now I'm coming to the features we used. So for this, we did a simulation of 1,000 different settings of a wind turbine with a diameter of 100 meters. We varied the pitch angle, this is the angle of the turbine blade, which is directed, as well as the rotation frequency in an area which is typical for wind turbines. Additionally, for second run, we added Gaussian noise as stated in the MEMS datasheet to see if the features are also significant when we have a kind of real setting. So these are the features. First, we got the rotation frequency estimated from the FFT. This is pretty straightforward. Next, we wanted to see what happens if we have periodic deviations from the circle, for example, due to this tower shadow. So we have two different features for that. We have the position of those peaks and deviations, and we have the width of those peaks. Next, we have the amplitude of the signal. And now I'm coming to the last two features. So we wanted to see what happens if the bending is different, if we fit different parts of the signal. So if we have, for example, we estimate the rotational frequency differently for the top part and for the bottom part and take the difference. That's the feature F top bottom we have here. The next thing, is what happens if we fit the right side of the rotation and the left side differently. That's the feature right-left we have here. So for these features, we wanted to see first if it works, if it's significant for our simulation. So we did a classification task with 400 samples for training and 600 samples for testing. You can see our results in the table down there with classification with support vector machines. You can see that the test error was very low, which is made us very happy. Although you can see that for additional noise, it gets more challenging to identify wind shear with those features. So now we wanted to see what happens if we take real data. For this, we took a 4-week real data set with this MEMS sensor mounted on the blade tip. The wind turbine had a diameter of 101 meters. And of course, for us, as in all real-world applications, we had to do some pre-processing because there were some missing values due to transmission errors. So these are real data. First of all, I have to say that we did not have any reference data to this, so we did some color coding. So we put the minimum rotational frequency and up to the maximum rotational frequency in different colors. So blue is low rotational frequency, yellow is high rotational frequency. Also, the feature shown on top of this is not the real feature since we don't have any reference data. So these are the features which were found useful to detect that effect in the simulation. First, now we check the extent of the features, if that's in kind of the extent is the same as in the simulation. And we found that this was the case except for this feature right-left, which we found. This is because we did not have any reference data, for example, for yaw mismatch, so we just had to guess any number there. So now you can see the features for the tower shadow here, and you can see that there's no real correlation in this. So of course that's disappointing, but that makes sense because we have fluttering on top of the raw signal in real data, and of course then the tower shadow is hidden in there. But if we move on to the other features, for example wind shear, we can see that there's a clear correlation here between our features and the color coding, so the rotational frequency. What we can observe here is that the feature top bottom, so the difference rotational frequency for top and bottom, decreases if we increase the rotational frequency. This can be due to a more balanced rotation due to the stiffening effect if the turbine moves faster. Also, you can see that the spread between right and left fitting here gets larger if we move to higher rotational frequencies. This leads to the conclusion that the alignment of the turbine is more difficult when you come to higher wind speeds. So last we have yaw and gravity here. You can see the rotational frequency on the x-axis and the scaling, so the amplitude of our sine wave on the y-axis. You can see an increased variance here for around 0.15 rotational frequency. This means that the alignment of the turbine seems to be more difficult there, so we have more turbulences. Also, you can see the trend going down of the scaling when you increase the rotational frequency, which can be explained with more bending when you move to higher rotational frequencies. So now I'm coming to the conclusion. We could show that there are correlations of these features we extracted with the rotational frequencies, which shows us, although we didn't have any reference data, that there are correlations and the features we found are significant. Also, we could draw conclusions regarding the stiffness of the blade, as well as possible mismatches of the turbine and the settings and the wind profile. So we can say that placing sensors at the blade tip is very promising for monitoring alternating loads and imminent fatigue. Of course, now it would be very interesting to compare those results to reference data. So what we will do as soon as we get access to the data is to check the features we extracted with reference to influencing factors. For example, you can imagine the wind speed, the wind profile, like unsteadiness or something, or also the pitch angle of the blades. So these are my references if you're interested later. And I want to thank you for your attention, and I'm open for questions.